Welcome to This Explainer. Today we are doing something really exciting. We're going to completely demystify how scientists actually design new molecules to treat diseases. And we aren't just going to jump in halfway through. We're building this up from absolute first principles. Even if you have zero background in biology or chemistry, don't worry, I've got you covered. If you've ever wondered how a tiny, invisible molecule can somehow cure a complex human illness, and how artificial intelligence is totally flipping the script on how we find them, you are in the exact right place. Here's a quick look at our roadmap for today. We'll start with the biological building blocks, unpack the difference between a disease and a drug target, translate biology into digital code, review the ultimate drug report card, explore the AI discovery pipeline, and finally, bring it all home with quantum physics and real-world lab testing.
All right, let's jump right into part one, the biological building blocks, from protons to proteins.
To truly wrap our heads around drug discovery, we have to zoom all the way down into the physical world, starting with the absolute simplest unit, the atom. Literally everything is made of atoms. The screen you're looking at, your body, a glass of water, and, of course, medicines. Atoms contain positively charged protons, neutral neutrons, and negatively charged electrons. And when these atoms connect, specifically through chemical bonds driven by how their electrons behave, they create molecules. Now, inside the human body, some of the most critical small molecules are called amino acids. You can think of amino acids exactly like a 20-letter biological alphabet. Just like you can take the 26 letters of the English alphabet and arrange them to write millions of completely different books, human biology uses these 20 standard amino acid letters to form long chains. We're talking chains that repeat hundreds or even thousands of times. But they don't just stay as flat strings. They fold up into these incredible, highly complex 3D specialized machines called proteins. And proteins are the actual workers in your body. They send signals, break down chemicals, and defend you against infections.
Moving right along to section 2, diseases versus drug targets, fixing the complex system. So we have our physical building blocks. Let's zoom out and see how this all stacks up into a living, breathing human. Atoms form molecules. Molecules like amino acids form proteins. Proteins do the heavy lifting inside your cells. Your cells group together to form tissues. Tissues form organs, and those organs, well, they form you. But what happens when something in this massive interconnected hierarchy breaks down? That brings us to disease. It is so important to realize that a disease, let's take cancer for example, is almost never just one single broken protein. A disease is a massive, cascading system failure. It involves hundreds of changes across proteins, cells, genes, and even your immune processes. Because of that complexity, scientists can't just target an entire disease all at once. Instead, they look for a single, careful control point within that failing system that they can actually influence. That control point, which is very often just one specific protein, is what we call a drug target. That takes us to part 3, the digital drug match. Let's translate this biology into code. Okay, so we understand the physical wet lab side now. We have a protein target, and we need a molecule to fix it. But to use artificial intelligence to actually discover that molecule, we have to transition the messy physical world into neat digital code. It's fascinating how AI actually sees biology. A massive 3D protein target is simply represented as a sequence of letters, an amino acid sequence. Meanwhile, a candidate drug molecule is represented as a text format called a SMILES string. For example, the SMILES string for ethanol is simply CCO. AI models can read these text representations incredibly fast, searching for that perfect match. But how does a text-based match on a computer actually translate back to reality? Well, when the physical candidate drug meets the protein target in the body, they don't just mechanically click together like Lego bricks. Since they're both made of atoms, their shapes, their charges, and incredibly, their electrons all interact according to the strict laws of physics. They are drawn together at a specific location on the protein, called a binding site, docking together to influence how that protein ultimately behaves. Which leads us directly into part 4, the ultimate drug report card, or what scientists call the multi-objective optimization problem. Finding a molecule that physically fits and binds into a protein's binding site is an amazing feat. So you might naturally be thinking, okay, the molecule that grabs on the absolute strongest is the automatic winner, right? Well, let's go ahead and shatter that misconception right now. A drug candidate actually has to pass what we can call the ultimate drug report card, and binding affinity is literally just one grade.
We also need potency, which is how strong the effect is, and efficacy, which is how well it works to fix the problem. Plus, a molecule might bind perfectly to our target, but what if it isn't selective? What if it binds to healthy proteins too, causing dangerous off-target effects? Then we have to consider QED, or drug likeness, and ADME. Absorption, distribution, metabolism, and excretion. Can it absorb into the body and match the right patient profile? Furthermore, if a drug causes toxicity, like a dangerous HERG heart rhythm, or if it has terrible synthetic accessibility, meaning we can't figure out the retrosynthesis to manufacture it at scale, its overall developability drops to zero. It completely fails as a medicine. Let's look at a really simple report card comparison to make this concrete. We have 3 hypothetical drug candidates here. Candidate A binds the strongest. It has excellent affinity, but it's highly toxic. That's a hard fail. Candidate C has strong binding and good safety, but it simply won't absorb into the human body. Also a fail. That leaves us with candidate B. Now, it only has moderate binding, but it's safe, and we can actually synthesize and manufacture it easily. Candidate B is clearly the best medicine, even though it wasn't the strongest binder. This crazy balancing act is what experts call a multi-objective optimization problem. Because frankly, no single molecule is ever perfect in every single category. So scientists look for what's known as the Pareto frontier, a set of candidate molecules that represent the absolute best available trade-offs across all these demanding categories. AI systems calculate an overall lead score, factoring in the AI's prediction confidence to help scientists navigate this frontier and find that perfect, delicate balance. All right, part 5, the AI discovery pipeline, taking us from a disease all the way to lab testing. So how does artificial intelligence actually orchestrate all of these complex report card grades into a real working pipeline? Well, it starts with the hardest part, analyzing the massive complexity of a disease and bravely selecting and validating a single biological target. Once we have that target, we represent it digitally as a sequence, maybe use an existing reference molecule as a starting point, and then we just unleash the AI. The AI generates hundreds, thousands, or even millions of totally new candidate molecules, spitting them out as those text-based smile strings we talked about.
Next, the pipeline shifts entirely to evaluation. The AI instantly throws out chemically impossible structures. Chemical validation? Check. For the valid ones, it predicts their 3D docking poses, basically guessing how they might fit into the protein. Then it evaluates the ADME properties to see if the human body can actually process them and predicts toxicity. It applies hard gates, which means automatically rejecting anything with high risks like HERG heart toxicity, before finally selecting the very best candidates to be sent off to a real-world lab. And that brings us to our final section, Part 6, Quantum Physics and Lab Proof. Time to model reality. Now, AI is blindingly fast at scoring those report cards, but to truly predict the future of drug discovery, we have to zoom all the way back down into the tiny electrons we started with. And I want to pause here to address a really common myth. Are electrons orbiting inside atoms like tiny little planets orbiting a sun? Not exactly. While gravity dictates planetary orbits, at the atomic scale, quantum mechanics takes over. Electrons actually exist in these complex, fuzzy probability clouds, not neat little circles. And this makes calculating exactly how the electrons of a drug will interact with the electrons of a protein staggeringly complex. This complexity is exactly why we are looking toward quantum computing. AI is brilliant, for sure, but it fundamentally learns patterns from past data. It's kind of like a student studying previous exam answers to guess what's on the next test. Quantum computing, on the other hand, attempts to calculate the underlying physics problem directly. By using hybrid models called QM/MM, researchers can use classical physics for the bulk of the protein while using quantum mechanics to simulate the literal, precise electronic interactions. But because this is so incredibly computationally heavy, these quantum calculations need a very precise setup: a 3D protein, a 3D molecule, a specific predicted binding pose, and they only simulate a tiny selected region right inside the binding site. It's a future refinement tool, not a perfect binding oracle just yet. In the modern pipeline, all of these incredible tools work together. AI acts as the massive funnel, screening millions of candidates in mere seconds. Classical and quantum physics act as the fine-tooth comb, refining the molecular docking and electronic interactions. But ultimately, you cannot cure a computer. The final step absolutely always requires real-world laboratory experiments to synthesize the drug and physically test the result. And that leaves us with this powerful takeaway. Drug discovery is not solved by algorithms alone. As the saying goes, AI proposes the ideas, physics checks the math, but experiments in the lab are what finally prove we have a cure. It takes a massive multidisciplinary effort to bridge the enormous gap from a single atom all the way to a life-saving medicine. Which leaves me with a final thought for you to chew on. If artificial intelligence can now help us rewrite the very alphabet of life by designing novel proteins and drugs, what incredible biological stories will we be able to compose a decade from now? Thanks so much for joining me on this explainer, and I'll see you in the next one.